Okay, so hi everyone. Well, first, thanks for inviting us to come and talk about what we do at CERN. I hope it's an interesting talk. My name is Ricardo. I work in the CERN cloud team. I've been at CERN for quite a while now. I joined as a student back in 2003, and I've done a lot of different things. So I'll try to give an overview of what the computing challenges are at CERN, what kind of technology we've been using over the years, and especially then focus a bit more on what we're doing. But I'll start by explaining a bit what CERN is about. I'm guessing that everyone has heard of CERN, but I'll try to give a bit more details on who we are and what we are doing. So CERN was founded, CERN is the European Organization for Nuclear Research. It was founded back in '54. And it has one main goal, which is to do fundamental science and to answer like big questions. What's 96% of the universe made of? Things like dark matter and dark energy that we can see, and we try to understand why we can see and what it is. What was the state of matter just after the Big Bang? A state called quark-gluon plasma, which we can recreate in our experiments. And why isn't there antimatter? Why don't we see it in the universe, even if theories that tell us that it should be there? So to answer these questions, we build very large experiments, some of the biggest scientific experiments ever built. This is the most recent one, and this is the biggest scientific experiment ever built. So this is the Large Hadron Collider. It's a particle accelerator, which is 27 kilometers in circumference. You can see here Geneva Airport, just to have an idea of the scale. It spans two countries, Switzerland and France. And it's made of like superconducting magnets where we accelerate protons. And we accelerate two beams of protons, one clockwise, one counterclockwise, and then we make them collide in these very specific places where we've built large experiments, ALICE, CMS, LHCb, and ATLAS. You can see, for example, this was one of the biggest experiments before, one of the biggest particle accelerators in the 80s, and now it's just a start for the big one. So we kind of build bigger and bigger instruments every time. And we try to recreate conditions that can help us explain what happened in the very first moments of the universe. So the CERN site is actually two parts. This is the one where we work. And then there's another one in the French side, and yeah, it's kind of a big place. Then underground, so the accelerator is actually 100 meters underground. There's a big tunnel. You can see the magnets here, and then there's an area where we can walk. This is often said that it's the coolest place in the universe, and it's literally the case, because to have the beams being superconducting, we have to cool it down to 1.7 Kelvin, which is very close to absolute zero. So we have very advanced cryogenic systems for this. When it's operating, of course, we can't easily access it. Right now is the best moment to come and visit us, because we are under maintenance until the end of the year at least. So you can actually go underground and visit the experiments. Then when we collide the beams, we've built these very large machines. This is the compact Muon solenoid, which is one of our detectors. It's not compact at all. It's 40 meters by 40 meters. It's also 100 meters underground, and it weighs 14 tons. You can see the people there to have an idea. So the beams pass in the middle. In this case, it's open, but then it acts as a gigantic camera. So it's not a camera as traditional camera, but what we want to record is what happens in these collisions. So it kind of acts as a camera. It takes something like 40 million pictures a second, and all these subdetectors will then generate a lot of data. So this machine will generate something like 1 petabyte of data per second. Of course, we can't analyze this. So we have hardware filters where we put this. We do a very big selection there. We cut more than 99% of the data. And in the end, it generates something like 10 gigabytes a second that we have to store, archive, and analyze using our computing resources. So this is a picture of what goes on. This is like from the raw data that we collect, and we have with the computing power we have, we try to reconstruct these events to understand what went on inside. All of this, and it's kind of the problem we have at CERN is that it's not like space exploration where we have like really fancy things to show. Physicists want this, which is just a plot. So all of this computing power, all of this data stored, and the result is something like this, where we have in blue the like predicted physics of based on the standard model of physics, and then you have the black dots, which is the actual data. And what we want to see is something like here, where the actual data doesn't match the theory, or doesn't match the known theory, but it matches some prediction, like the Higgs. So that bump is the Higgs boson that we saw the first time in 2012. So it's kind of underwhelming, but it gets physicists very excited. We have other experiments. So if you walk around the CERN site, you will see that it's not only about particle accelerators. So just down the road from where we work, there's the antimatter factory, which is also a pretty cool place to go visit. And then we have also a machine in the International Space Station that was launched a few years ago, and we have it's operated by CERN. Some of you might have heard of CERN also because of the World Wide Web. All this computing needs, what this generates is not only the need to develop new systems and explore new technologies, but also the need to share information between the people on site. This is what triggered the World Wide Web in the end of the 90s and the end of the 80s and beginning of the 90s. So the need to kind of label data, link to it, and kind of share between the collaborations. This is the picture of the initial proposal. You can see it's all about sharing and kind of labeling things. Now I go more to the technology and computing part. So to process all of this data, I mentioned that the detectors will generate something like 1 petabyte a second. We reduced to 10 gigabytes a second. We have Beam running pretty much all year, or we try to as much as possible. We end up generating something like 70 petabytes a year, which is a lot of data. So we need a lot of computing power to process this. We used to have 2 data centers, one based in Geneva and one based in Budapest. We're actually consolidating our resources into one single data center in Geneva at the CERN site. The data center today is managed by a private OpenStack cloud. It has close to 300,000 cores, and it has this is just the storage for the cloud, which is 15 petabytes of disk storage. The actual physics data is stored in another system, and we have close to half an exabyte of data today. The cloud is used by a lot of people, so we have 3,600 users, 35,000 virtual machines, and 10,000 hypervisors, so physical machines. And one thing that I will mention after is the Magnum clusters there, which is a container-based infrastructure, which I'll talk about more after. So it's not a hyperscaler, it's not Google, Amazon, or Azure, but it's still a pretty relevant data center. Now, the issue we have also is that this is not enough. So all this capacity is not enough. So over the last 20 years, we've built something called the Worldwide LHC Computing Grid, which is where the reason I joined CERN initially was to help with the development of this. And what we tried is kind of a pre-cloud thing where we tried to do, it's called Grid, which is sharing resources in the same way we share data using the web. We wanted to share resources between the different institutes that collaborated with CERN. So we ended up connecting more than 200 sites around the world. And the total capacity with this network puts us at 700,000 cores. So it's like more than doubling our capacity. If you look at it, you will see that there's something like 400,000 jobs running all the time in parallel. So it's very, very much used. So, and then if we go back in past, a bit of computing history. So in the 70s, I didn't live through this, but when I arrived, there was still one of the Crane mainframes there that we can see in the corner. And it kind of I'll try to show that if you visit CERN, you also see a bit of the history of computing there, so it's quite interesting. This is how it looked in the 70s, where people actually worked inside the data center. Then we transitioned to commodity hardware, like literally, because all we did was buy desktops, and this I already lived through. We bought some kind of IKEA-like shelves, desktops, and we would put them in racks. It was very inefficient in terms of power and cooling, but it was cheap. So we lived through this for a few years, but very quickly we reached limitations, so we transitioned to what is today our data center that looks a bit like this. You can also see here in this picture the tapes. So this is always a question we get is, do you actually still use tapes? We do. We archive everything on tape, and we have the tape robots here. So this one is gone, but this one is still there. We have 400 petabytes of tape storage where we keep at least one copy of all the data we have. And then this is a small computer, but it has a lot of history. So this was the first World Wide Web server. When Tim Berners-Lee created the World Wide Web, this is the computer he has under his desk. It was a very important computer, and he made it very clear by putting a sticker there that said, this machine is a server, do not power down. And the reason he did this is that a couple of times the people cleaning in the evening, they would unplug the server to plug the vacuum cleaner, and the internet would be down, or the web would be down, not the internet. So he made it very clear by here that this is not acceptable. So the topic of the talk is the transitioning from physical to virtualization to containers. That kind of hopefully gives a hint on how we are moving and where we might be going. So if we look at what we've done until, let's say, 2012 at CERN, or 2010 at least, we were basically doing just physical machines, just bare metal. And this had many limitations. So if I kind of divided into a couple of categories here. So if you look at provisioning, to get a machine, you would open a ticket or a few machines, and then someone would have to actually go into the data center to finalize the provisioning of these machines, maybe even buy them if required. This could take days or even weeks to get the resources you were asking for. Not very DevOps, so let's put it like this. And then maintenance was also highly intrusive. Like, you had a very limited set of physical resources. If there was a need for some maintenance there, you would lose a fraction of your capacity, and it could take days again for it to come back. Deployment and updates, I put here minutes or hours, and it's kind of like this. We're already using systems very similar to what Puppet or Chef do, just previous generations of those systems, and we could deploy in minutes or a couple of hours if you had to do some more complex setup. And then the utilization was a big issue because we had a lot of people wanting to run very low traffic web applications, and they still asked for like a full physical box that might have, I don't know, a few cores, a lot of memory, and then it was very hard to share this with other people. So in this aspect, it was pretty bad. Then around 2012, we started doing virtualization. And here it helped, especially in the provisioning. So when I talk about cloud, it's more the fact that you can do an API-based interaction with the resources, where you can allocate resources, compute resources, storage, everything you want. So provisioning became much better because you already had all the hypervisors set up, and then you just interact via the APIs with the systems, and you get the VMs very quickly in a couple of minutes. Then maintenance, we do live migration. So if we have to do interventions in the hypervisors, the system will allow us to just live migrate the workloads to a different box without the user seeing. In most cases, a couple of cases doesn't work. So that's why I say potentially less intrusive, but in the general case, this is possible. Then deployment and update, not much changed, but utilization changed dramatically because you can overcommit resources. So you can just lie about the amount of resources you have in the hypervisor, especially for CPU. For memory is a bit more complicated. So here we, internally for the generic services, we overcommit by something like 4 times. But if you would deploy OpenStack from scratch, the default is actually 16 times, and it works quite well for most cases. For the compute intensive, we don't do this. So a bit of details of the OpenStack private cloud. So it's a big deployment. We have 10,000 physical machines. And we reached some scalability issues. So this is the option, the decisions we made, which is to separate the deployment into 3 separate regions instead of having one region in one data center. We actually, in the data center, we split in 3. This allows us to scale the control plane much easier. It also allows us to gradually deploy new versions. If we need to perform upgrades, we do the less critical regions first, and then we gradually move to the critical services and build confidence with this kind of deployment. And then within the region, we also split the infrastructure into multiple pieces. In here, it's also for scalability, but it's also in terms of capabilities. So if we have GPU resources, then we put them together and we put them in a cell, and then the scheduler will know where to put things that require GPUs. Usually what we do is we have 2 times per year where we buy hardware, and then we'll just group it together and make a new cell out of it. And then the same when we retire hardware, we just retire full cells in one go and we migrate to workloads. So this cell concept allows us to partition the data set into this kind of common blocks or homogeneous blocks, even if the cloud is very heterogeneous. We used to run 2 hypervisors. These days we run KVM only. The other point that I would highlight here is that all of this doesn't come from one day to the other. We say often that it's an evolution. We don't really have revolutions in our infrastructure. If you look at it, we introduced the cloud in 2013. It became production around that time. And then gradually we were having more and more resources migrating from the traditional deployments we had to this cloud-based deployment up to what we have now, which is around 10,000 hypervisors. So this also helps the service managers to get used to this idea of using new APIs and kind of delegating the management of the resources. People are very attached to the physical resources, but they need to build confidence to let go. And the same for virtual machines. So some numbers. So here actually it stops in 2017, but it's almost 30,000 VMs already. And if you look at creation, we have a very high creation and deletion cycle. I think by then we had something like 6 million VMs being created. So there's a lot of workloads that create a VM, do something, destroy the VM, and do this constantly. So we need to scale to this kind of workload as well. So how to manage all of this, it's really automate everything. We have a limited amount of manpower. The operations team of the cloud itself, I'm not saying the whole data center, but we are like 6 people, and we were 6 people at the start. So kind of we transitioned also our roles from being more experimenting features and adding new features to the system to making sure that everything is automated and that we can scale to this kind of level. So 2013, we also introduced Puppet, and this is still the core of all the configuration system at CERN and deployment. We run the control plane itself on virtual machines as we gain confidence in our system. The system is kind of it has a couple of physical machines to bootstrap, but the whole thing runs on virtual machines. Most services also run on virtual machines and are configured using Puppet. And then the daily operations, so we also don't do pretty much anything manually. We just like only tricky tickets we had to look. Onboarding new users, people asking for new projects, code updates, special capabilities they need, like access to GPUs or special networking roles. Everything is managed by our workflow systems that are based in Rundeck, and then there's also an OpenStack project called Mistral, where we also do this. The other thing is resource usage, and here we put a lot of effort into understanding where and how to best overcommit the resources, and we do preemptible instances. So if you're familiar with the Amazon spot market, it's very similar, but instead of having like a market-based price, it's more like a low SLA VMs where they can only last up to 24 hours, and there's no guarantee that they even live that long. We also backfill everything, so whenever we can't overcommit for some reason, we make sure that if the resources are not used, we put some analysis jobs running on the back. So this is virtualization, and then because I also work a lot in the container area and networking, I'll be very biased here, but if we look again at the categories, this is a real breakthrough. It's, if you experimented with containers and you were doing virtual machines before, it feels very different. So provisioning is literally seconds if you have it well set up. Maintenance is very easy. And the main thing where maintenance is easy is not because containers itself are that different from virtual machines. It's really because the container orchestration systems, they oblige the applications to expose a lot more about their characteristics than what you do in a virtual machine. A virtual machine, you basically get a similar access to a physical box, SSH, root access. In a container, if you do it with Kubernetes, you have to express a lot more about your application, and this allows us to do a much better job about moving stuff around in the cloud and making sure that everything operates correctly. So deployment and update is also a main difference, and utilization. The reason it's better than virtual machines is because CPU-wise is pretty much similar, but because we don't have this kernel, extra kernel layer, we recover a lot of the memory in our resources. So if you think on one box, recovering the memory used by the extra kernel is not a lot. If you think of a data center of 10,000 boxes, every bit of memory, it will be a lot. It's something like 3% more we get out of memory back. So the orchestration system we based on is Kubernetes. So we actually started by supporting multiple ones, but today I think the bet is Kubernetes. It became the base API for all kind of deployment like this. You have a lot of options. This is one of the advantages, is that you don't have to bet on one tool or not one tool, but one infrastructure. You can decide to use any of the major cloud providers. You can decide to deploy it on-premise. And also, you have one advantage, which is if you want to use a managed deployment, like what Google offers with GKE, you can. But if you want to deploy and manage your own, you can also do that. So we kind of saw it as an opportunity to finally have a common API to define our infrastructure in all the areas. I summarize here. So we actually, on-premise, we deploy using an OpenStack tool because we already have an OpenStack infrastructure called Magnum. And then we depend on all these other tools. So, of course, Docker and Containerd for the core runtime and the management of the containers. We use Helm for the configuration and deployment, Prometheus for the monitoring, and then we have FluentD for the log collection. And we use Envoy, but we also use other ingress controllers like Traffic and Nginx. So we support a few. So I mentioned this. This was a kind of a complicated transition because at the time it was very hard to decide what to use. So we started by offering our users all the options, which was a kind of a challenge. But so they could decide to create a cluster with any number of nodes, and they could decide which orchestrator they want: Kubernetes, Swarm, or Mesos, DCOS later. But there was a clear winner very quickly. So out of, I don't know, 500 clusters we have today, there's a few Swarm ones for very specific use cases where you need the Docker API compatibility, but actually the majority is Kubernetes. So I don't think there's a question today on this area. Then I don't know how many of you have heard of GitOps, but it's actually something we've done for a long time. So all the configuration for our services, for our infrastructure, is defined in Git, and we push everything to Git. We were already doing this with Puppet. All the manifests are there. All the data for the configuration of each of the clusters is all stored in Git. And then the machines will, when they boot, they know which area they belong to, and they will just pull the configuration they should belong to. So for Kubernetes and containers, we did something very similar, where we use Helm. We push all the Helm manifests and the values files into Git. And then we have tools. In this case, I put an example with Flux, but actually other people use other tools that will pull the data, the configuration that should be deployed in the cluster. And this mapping is done externally, so you can do this in multiple ways. This has some advantages, which is you don't have to put any additional information about the cluster, like credentials or anything in Git. Just on the cluster, you say you should deploy this application in its namespace, and it will pull, and all the authorization and credentials is already handled by Git itself with the normal Git permissions. One thing that it's not clear yet for us is that because we had all this flexibility on the deployment, we started by allowing people to deploy one cluster, have their application, and run one application in their cluster. This is not optimal, of course. So it's not optimal in two aspects. One is that if the cluster breaks, their application is dead. And the second one is that for resource efficiency. So what we are experiencing now with is this second option, which is you have one application, but you have multiple clusters. Maybe instead of having one big one, you have multiple ones. And this kind of gives you high availability, but it also gives you a reduced blast radius. So if you have an issue in the data center, it's very unlikely that the 3 clusters, if they are well spread, that they will all be dead. Also, it gives you, again, the same confidence of upgrading one cluster at a time without impacting the whole capacity. Maybe you will impact a subset and lose some capacity for a while. But overall, your application stays up. The ideal one would be to have this third option, which would be the infrastructure team would manage the cluster, and the service managers would manage their service configuration. And then where each application runs would be managed by us directly. But this requires some coordination that we haven't completely set in our teams yet. And for finalizing, I'll just give an example of some scale applications. So we run all sorts of things at CERN. We have a lot of different teams. We run WebLogic, we run I don't know, Tomcat servers, we run Python applications, we run all sorts of things. But the core is doing data analysis. We have a lot of data to process. So one thing that Kubernetes also allows us is opens new doors to what we can do in terms of using external resources. So this was always a problem. If we want to use the public cloud, they all have their own interfaces. If we want to use supercomputing centers around the world, they will also have their own batch systems and their own interfaces. So kind of this idea that Kubernetes became the language that everyone seems to expose kind of opened up some potential here. And this is very important for us because we have spiky workloads coming throughout the year. Very often the big physics conferences are around the summer. And suddenly, like, all the physicists want to analyze their data sets, and we can't over-provision to cover for this. So the idea would be to find a use case where we could try to see, can we extend our data center in a very short period or in a larger period without too much effort by trusting the Kubernetes API. So we took the challenge, which was to take the Higgs dataset, the one that led to the Nobel Prize in 2012, which is made of 70 terabytes and 25,000 files. And the idea was to do it on stage at Kubecon and redo the analysis live. The original analysis took more than 20 hours. We had like 10 minutes to do it, so we needed a lot more resources. So here I put already kind of the structure that we did at the time, the cluster creation to create a large cluster. I'll give details after, and then pull the images. But then we had, on stage, we had the data download and the processing time, and we could actually do it in under 5 minutes. So we started by trying it out at CERN. We pushed the 70 terabyte data set to S3, which is backed by Ceph at CERN. Then we had a Kubernetes cluster that was running 25,000 jobs. Ideally, because these are single core jobs, we would have 25,000 cores. We have 300,000 cores available at CERN, but somehow they didn't give us 25,000 cores to run a demo. They said there's other stuff to do there. So we had to fish somewhere else. But we could run a trial where we would push the job results to Redis and then visualize using Jupyter. And then we have a partnership with Google, and Google was very happy to try this with us. So we pushed, again, the 70 terabytes data set to the equivalent of S3 at Google. And then we created a cluster at GKE, and we actually created a cluster of 25,000 cores there. And it was in a single region, but in three different zones to maximize the throughput. And then we could run basically 25,000 jobs in parallel. So the time of each job would be the total processing time, which is pretty spectacular. Then we would push the results to the equivalent of Redis, which is the Google Cloud memory store, and then visualize using Jupyter. So just to finish, I'll show the screenshot of the build. So we did this live, but you can see it's sped up. But each dot here is one job finalizing, and we're basically what this shows is that instead of like of course we will still need a big data center at CERN because we have a lot of 24/7 workloads. But if you think about it, anyone with the cost of this is something like $250 to run the full analysis. So anyone with a couple $100 can do like the full physics analysis for the Higgs dataset, which is pretty large. And this opens up a lot of new ideas for us. And this is all because of this new tooling, this modern tooling like Kubernetes and all the ecosystem around it. We can explore a lot of resources outside. We don't have to only build our own systems and trust our own resources. We can explore what's coming next. And that's it. So I'm happy to answer any questions, and I hope it was a good enough overview. Okay, the question was if we actually test the backups. So we do backups for physics data, and that's the large chunk. But we actually also back up our databases, and we do run regular like recall from tape. There's a lot of experience of tape handling at CERN. We actually used to have a hierarchical file system where every single file at CERN would go to tape first and then would be recalled to disk every time you would read it. This is not very fast, of course. So these days, we use it really as a backup. But at the start, it wasn't. It was really like a hierarchical file system. But the other thing is that we actually have some tapes that are 30 years old, and they still work. So those are the reasons we still use tape, is that we know we can trust them. They're cheap. They don't consume any power. Like the market is kind of shrinking, so there might be a need to change in the future, but for now, we trust them.
You are showing new tools that were happening some years ago. How were you doing between the time the CERN was created and the time where those tools were appearing?
Right, so that's a very good question. So like this is a gigantic transition for us. So what I mentioned here, and this is where I was working. So all the systems to build a gigantic distributed infrastructure with more than 200 sites, we built them in-house or with collaborations with similar institutes. And this was a large effort. There's a lot of code there that has to be maintained. And like right now, suddenly, because of the public clouds and the interest that suddenly was triggered on the open source communities in this area, we can start migrating to something that a much larger community will maintain. So instead of, this is happening in all the areas. It happened in the compute and orchestration. It's happening in storage, where we have things like Ceph that we can use instead of in-house systems. This is it's also a big change internally, because instead of hiring so many developers, we need to hire more system operators and administrators. So it's a big transition.
Have you considered using another YAML templating other than Helm, with Flux, for example?
Yeah. So this Puppet was kind of enforced, I would say. There's unhappy people that still use Ansible in a corner or something, but like the majority is using Puppet by decision, like upper level decision. And the reason for this is basically to spread the knowledge, to have more people that can do this. Yeah, but we kind of also learned a lesson that in some cases, it doesn't make sense. There's too much effort to mandate this. So for Helm, we don't mandate it. It's the one we advertise the most and that we provide support. So we organize, for example, we call it cloud office hours, where people can show up with their tooling and we help them to get it going, like 80%, and then they finish. And we do this for Helm. So it kind of promotes this idea of one tool, but it doesn't mandate. So there's people using Customize as well. There's people using their own scripts to generate templates. There's a bit of everything. But if you use Helm, you will have much better integration in the infrastructure.
You got me intrigued in something. Are those 6 human guys that do the operations or 6 ET guys, extraterrestrial guys? You mentioned 6 guys.
No. Yeah, that's why I. No, I don't want to brag. Not at all. It's the 6 people that do the OpenStack and the cloud control plane. So it's not the people doing the storage. It's not the people doing the data center operations. It's not the people doing the networking. In reality, our IT department is structured in a pretty traditional way. I would say we have the compute team, that is my team, or the team I belong to. The networking team, the data center operations team, the storage team. And when I say 6 people, it's the people doing the OpenStack part. For example, for the Puppet part, we have like 2 people more that do the Puppet master maintenance and all the life cycle for this. For the core Linux, we also have a Linux team. If we have an issue with Linux, we have Linux experts that can help, like 1 or 2 that are always there. And then the data center, it's a lot of people. So it's
How's the team size? All those.
The whole department is 200 people, but this is the computing for the physics, but it's also the campus. So at CERN, on any day, we'll have 10,000 people on site, and you have the wireless systems, you have like the phone book, you have all the systems that need to be maintained. This is also managed by the IT department. And in reality, we have more than 60,000 users because pretty much every physicist in the world that is linked to any collaboration like this has a CERN account. And this is something that is very specific. So for example, our mail server puts a lot of challenges because we have tens of thousands of users.
Thank you again, Ricardo.
Thank you.